My name is Jason Sonnenberg. I'm the lead developer of the chemistry education team, and I'd like to share with you what we've been working on for the last year. I've got some things that are already available and a preview of some things that'll be rolling out towards the new year. So as you may know, we have quite a few tools that are useful in chemical education and research. The most new one is the Wolfram GPT, which we'll talk about a little bit more. Of course, that's the probabilistic tool and based on LLMs. And then we have the Wolfram Alpha deterministic AI, and then of course the language and the demonstration projects, which are quite useful for building in-class activities and activities that could be used at home in the classroom. We also have the Wolfram example repository, which is growing by the day with more examples in the area of chemistry. And then of course our function repository and our Packlet repository, I'm sure will be talked about by the other chemistry team members. We have an ever-growing list of resources there. I think the function repository, we're up to something like 68 functions, 65 functions. So we're growing leaps and bounds. What I'd like to do is, before we dive into the tools, and we won't talk about all of them, I'd like to also share with you what we've been doing in getting the word out to the chemistry community. So this year has been very busy. We have gone to quite a few chemistry meetings throughout the country. Most recently, we were at the Fall National Meeting in Denver. Before that, our big push was to attend the Biennial Conference on Chemical Education. This is a meeting that occurs every 2 years and pulls international chemical educators together, about 1,000 of us, I believe it was. And then, of course, we have our summer research program. We went also to the Mid-Atlantic Regional Meeting over at Penn State University and the Molecule Meeting that were both hosted there at the same time. We did the Spring ACS meeting in New Orleans. For those of you that aren't chemists, the ACS meets twice a year nationally. So these are big events. For example, the spring meeting brought in 17,000 chemists. Then we've also done talks at the Lehigh Valley American Chemical Society local section meeting, and also spoke to the School of Sciences at the Sony Oneonta. All of these have been very productive conversations with chemical educators and chemical researchers to get the word out of what we're building and what we can do with those tools that we've built. Very excited to report that for the first time, we had a Wolfram booth at the BCCE meeting down at the University of Kentucky, and it was very well attended. We had, we were open for 4 days, and we had quite a few folks coming by. The spikies were very popular, so the chemistry community is slowly getting populated with not only our spikies, but also our technology. So we're really excited about these efforts to help get the word out of all the amazing things that we can do in chemistry with the tools that we've been building. Besides getting the word out of what you can do with our tools, we also run a summer program, actually two. We run a high school summer program, the Wolfram Summer Research Program, WSRP, and we also run a program for adults, the Wolfram Summer School. And in both cases, we have chemistry projects. So Bob and myself are the leaders of that effort. And this year we had a record-breaking number of projects. Last year we had 7. And our previous record before that was 5, and we've totally blown it away with this past year. We had 10 different projects, and I'll go through those quickly. These are all available on Community Post, and if you just search for WSRP or WSS, you'll be able to find them quite easily. So Amaya was looking through molecule cages and building them up systematically using our pattern reaction tools. Then Sinhora was working on a collaboration with me and the folks at Hopkins, looking at bonding in polysaccharide molecules, using, again, our tools inside of molecule value. Sarah was working on reaction classifications, and we'll get back to some of this. Her work has been pushed out into the Wolfram Alpha project and resulted in 2 WFRs, which we'll show you in a moment. Ananya was doing carbon nanobelts, making very large shapes of different sizes and systematically generating them again using our pattern reaction tools. Annie was looking at amino acid sequences and the shapes of those resulting amino acid sequences. William was looking into inorganic properties and particularly looking at isomerization and coordination complex, being able to figure out the symmetry labels for various complexes. He also was able to create a function that's in the function repository. Tony was looking at a pharmacokinetics project, which is one of the newer ones in this area for us. We haven't had a lot of pharmacokinetic projects, but we're really excited about Tony's work. Pavel was looking at isotope decomposition in radioactive material from supernovae. So this is a little bit more physicsy, but again, you're looking at radioactive isotopes, so that's chemistry. Nicholas was looking, and Nicholas was in the summer school, so WSS, to find his community post, was looking at multi-way chemical reaction networks using chemical space networks. He was mentored by Bob. And then Julian was doing aqueous electrolytes with peptide additives, and they have a presentation later, let's see, I think on Friday, but we'll come to that in another slide. So we're really excited by those 10 projects. And like I said, oh, sorry for the size, this is a little small. We have 4 new resources, 3 WFRs and a Packlet. So let's slide over and take a look at what those are. So we have the coordination molecule stereochemistry function that you can pass in molecules and then figure out what the stereochemical label. So this would be a cis isomer, for example. And this would be the trans isomer, similar to what we see in organic chemistry, but then we get more complicated situations when we get to octahedral cases and such. And so we can get the Fock and the Mer isomers detected now. Elementary reaction type allows us to determine if the chemical reaction that's represented by the chemical reaction or the pattern reaction is potentially an elementary reaction. Of course, experimentally, you must determine the elementary reaction type, but we can predict based on what the information is provided to us, and that's what this function does. We can also compute the reaction molecularity, which is the number of balanced reactants that are used in the reaction. So again, you can pass in chemical reactions or pattern reactions and compute this value. And then lastly, but not least, is Bob's molecule complex Packlet, which allows interactions between multiple disconnected molecules. In this case, here we have a picture of water molecules acting as a solvent to a bigger solute. And Bob will be talking about this again on Friday. So we're really excited not only about the 10 projects, but all of the new tools that they created. So part of the conversation that's been happening at all those conferences throughout the last 12 months has been about the newest tool in our line of tools for chemistry, and that's the Wolfram Custom GPT. Now, while this community here at the conference today may be very comfortable with the idea of LLMs and the technology that it incorporates, a lot of chemists, particularly chemical educators, may not be. This is because they have a specialty in other areas, namely the education, and catching up on the latest and greatest tech can be a bit slow. And all the universities aren't necessarily equally training their faculty on the new tech. So we often think about, well, can you explain it to a student? And a chemistry instructor clearly can explain how to balance a chemical equation. We have a lovely explanation for it through our step-by-step features. Also quite common, most chemical educators would feel very comfortable recording an uncertainty from a laboratory measurement. We represent that in the language using an around inside of a quantity object, but this is quite common, and most people are in the chemistry field aware of uncertainty. Now, for those that teach in the physical chemistry area, this is where you first start running into probabilities. And computing expectation values for a given wave function. The majority of first year, second year instructors will not necessarily have this under their belt. And then, like I said, the majority of my colleagues at the conferences said that they didn't know how to explain ChatGPT or the other bots. And this causes a bit of a problem because both the faculty and the students are already starting to use it and not really having a firm understanding of what's going on behind the black box can be a little dangerous and also not necessarily lead to good results. Um, as you may know, ChatGPT is an always evolving, updated LLM by OpenAI. It has a finite limit to the newest information that it has. When I asked it last, it was 2023. And again, it can generate text in multiple languages and interpret a variety of other inputs. And if you haven't played around with it, you can use the QR code here or go over to chatgpt.com to play around with a free account. And that's what a lot of students and faculty are doing. But again, as I said, there's a generally broad misunderstanding of what's going on because chemists and most folks actually maybe that aren't in the tech field don't do probabilistic computing. And so, you know, the difference between deterministic computing and probabilistic computing can be, you know, not intuitive and is behind what's going on. And of course, Stephen has a great article explaining this in more detail that has been very popular in the at the conferences and at the booth at the BCCE. But when it comes down to using LLM tools like the Wolfram GPT or just ChatGPT in general, it's important to understand what you can do with the tool from a chemistry context. And one of the most fundamental things that non-chemists or new students coming into chemistry struggle with is visualizing molecules. And we can see that if you're asking the question, you know, what does the structure of phenol look like? Let me remind you, this is what phenol looks like. It's a benzene ring with an OH group attached to it. There's hydrogens off of each of these vertexes that are not displayed in this picture. But as chemists, we understand them to be there. So we get a little lazy and don't necessarily iterate that explicitly. Now, if you go and ask ChatGPT 3.5, you often get some sort of response that looks like this, and sort of a little structure diagram in ASCII text, which, as you can see, this is clearly not phenol. So there's limited usefulness here, and the description is usually correct, but that if you can't visualize things or are new to chemistry, that's not really going to help much. Chemists really are visual folks. So if you go to the latest and greatest, ChatGPT 4.0, you get some better results, but not much. Here it got a little bit more creative and tried to do a ring, but yeah, still no good. Not helpful for, you know, bringing up new chemists into the field. However, if you use the Wolfram GPT, where it now we've given deterministic tools to the probabilistic LLM, then it gets much better. Much like a student, when we give students calculators and other reliable resources, deterministic resources, their performance improves too. And so here you can ask, what's the structure of phenol? And you get the structure back. Quite lovely. Now, this is just a simple case. You can do much more complicated things. I don't have time today to go through all of those. But what I do want to share before we move on to some other topics is that prompting is critical. So not only are the chemistry tools in Wolfram language new to you, the audience, and all of us that are using the language, because they've only been around since version 12, and we're still rolling out new ones even now. So not only do humans need to learn about what's now available, but so does the LLM, which means that your prompting for using the LLM to do good chemistry needs to be a little bit on the verbose side, because you basically need to remind it, hey, these are there, and you probably haven't ingested enough information off the internet to know about them. And if you're willing to use a slightly larger prompt and give short little examples of the functions that are available, you can get much better results. So here is a case where I was doing visualization. I told it what functions are available. Notice that some of these are built in, some of these are resource functions, but if you tell about all of it, it will use it, well, hopefully. And you can see what that gets us. So of course, you're always going to get a very large output as it regurgitates what it took in, but then you can just draw the 2D structure and it gets it. And you can do more important things like highlighting substructure by telling it, look, it knew what a hydroxyl group was and it went and highlighted it. Now it can go from 2D to 3D, which is often the tricky thing for folks to do. And so you get the other representation right off. With limited, you didn't have to do a very large, input. It just knew what to do because now it has some understanding of the tools that are available to it. And you can go from representations. Here's this ball and stick representation, and go to more of a 3D space filling representation, showing more of the electron density each of the atoms occupies. So you can see that with a bit of work, you can get better results. I'll have the notebook available that you can look at the chemical conversions, but in the interest of time and staying on schedule, I'll move forward. So Wolfram Alpha, we've been growing the content. You may not be aware of it, but there are quite a lot of aggregation states that are tracked in chemistry. And so the common ones, solid, liquid, gas, you may be familiar with, but there are quite a bit of others, absorbed, amorphous, aqueous, condensed, and so on, that one can use when putting together a chemical reaction. Those are now all accessible in Wolfram Alpha. This is currently live. You can put these into your chemical reaction and they will be parsed and carried along and also come out in the resulting control equal input. We also have improved the balancing output. So when you give a silly reaction, like in this case where we have ferrocene and then going to silicon, this is not something, and as you can see here, there's other aggregation states, amorphous and fluid. And this isn't balanceable. We don't have iron on the product side. And that's now the message that comes back. So we're trying to be more informative to the learners who might be trying to balance chemical equations or possibly mistyped and didn't cut and paste everything in. Same if things are missing in the reactants. So, yep. Well, my example doesn't have the right message, but anyways, we have output now that talks about unbalanceable reaction and gives more details to the user. And if you happen to do a reaction where your charges aren't matching, you have a neutral species going to a charged species, that obviously is not balanceable. You've lost track of some electrons. And so we give information about that now too. The engine, the balancing engine has been updated to do that. Let's see about. All right, so we have some new content, the step-by-step. So we've expanded our aromaticity results. We now have results for molecules that are not aromatic. And so we explain, going through the similar process, but explain, yep, no, not aromatic. Same with our aromatic atom count. We now can call each of those properties separately and get the results with a full explanation. Let's see, hopefully this doesn't take too long. So we step each of the users through identifying the different atoms and then looking in the rings and excluding different bits and then counting the electrons and finding the rings. So that's been improved over the last year. We've also made sure that our particle count properties, so the number of electrons, number of molecules, number of protons, has been updated and expanded. So now it works fully with chemical formulas, explaining what's going on there. Then we updated the molecule count to be in line with IUPAC. So if you're talking about an element that, it's a single atom, you can't convert that to molecules because molecules are by definition things that contain 2 or more atoms. Our proton count was updated. And the other fun thing that we now have is that the unit conversion pod, and this isn't all just the chemistry team's effort, this is the effort of others, now have step-by-steps for explaining the conversions in the unit conversions pod that comes out for chemistry queries. And you can see that it steps through everything nicely. Our calculators are some of the highly used aspects of Wolfram Alpha, and we're now up to 65 of them, which we're quite proud of. We've expanded the Nernst equation. It is now supported by step-by-step results. And this, gives us our first step-by-step support for electrochemistry content. On Avogadro's law and Boyle's law and Bragg's law, we have these beautiful new schematics that explain the concepts further, and hopefully will be very useful for our students. Charles and Graham's law also got some nifty graphics. Out of the collection, we are about 80% of the 65 calculators that we have step-by-step support, and we're hoping to increase that going forward. We've been working on chemical reactions. And this material that I'm showing you now will deploy to the public servers in January. But we've done a lot of work to move forward. So let's back up and start with kinetics. We've applied the molecularity and the elementary reaction type properties that Sarah worked out the WFRs for. We taught Alpha how to do that, and Sarah's WFR functions will be the mathematical inputs for these queries. And again, that'll roll out in January. We've done some work to be smarter, teach the engine to be smarter when you accidentally give two products that are the same or two reactants that are the same. Those are handled properly and collapsed in the balancing and then carried through the rest of the output. We've improved our support of errors. We've done all, revamped all of the code underneath, and we now carry through the type of reaction error that you give us. So here in this example, we've got the net forward reaction arrow. You can input the bidirectional, so a reaction that goes in both directions, but not necessarily at equilibrium. Then we, of course, have the equilibrium arrow. And note that we're following IUPAC standards. So this is the equilibrium arrow. So I know there are two in the language, but IUPAC uses this one, and so we carry that through as well. And then you can also do stoichiometric reactions where it's the long equal. And again, that's propagated through all the reactions now. And also, we're very proud to say that we've got what seems like a simple problem for balancing, but half reactions were a little bit tricky. The engine now handles them and balances them just fine. And this will open up quite a bit of things that we can do going forward with redox chemistry. And I'm looking forward to reporting out on that this time next year. In the Wolfram Alpha Notebook Edition, we've got all the translations for the reactions. Now, rather than giving a Wolfram Alpha pod, you get the chemical reaction objects with and without phases, and you can balance and get the reaction balance output. The reaction balance will be coming out next month. The previous two examples here for chemical reactions are live now. And again, we expect this to grow when we see each other again in 12 months. So I'm not the only one presenting. The chemistry team has quite a bit of content for you to take in. We have two talks tomorrow. Sutik is talking about the biomolecules. I've got another talk on a research application. Jason is also talking about quantum chemistry tools, which we're really excited about. It builds and will make the sort of things that I'm talking about at 1:30 much easier with his new tech. Bob is talking about the summer project with the molecule complex. You should check it out. And then David is doing some really interesting stuff with OpenStack's textbooks and regs that could be used in chemistry, both chemistry education and chemistry research environments. And with that, I'd just like to point you to some useful links. Our chemistry core areas is growing. Check that out. Our dilution calculator, which I've spoken about in years past. Our fast introduction for chemistry students. If you're incorporating our tools into your chemistry class, you and your students might find this useful. And then, of course, our ever-growing chemistry resources, which is one-stop shopping for everything that we offer, from student talks to chemistry team talks to calculator links, all that stuff. It's fun and it's there. So I encourage you to check it out. And with that, I'd be happy to take any questions that you have. Thank you for attending.